It is my honor to introduce our second speaker today, Eva Czabarka from USC. She's going to talk on orthogonal arrays and transversals.
Thank you. So I'm going to see how much what I'm planning. I'm going to get through in 25 minutes. It may not be all. I'm going to talk about orthogonal arrays and transversals, and they pretty much turn out to be the same. In the abstract, if you've read it, I've mentioned the background Sperner theorems where we were coming to this. I'm not going to talk about that because that would take way too much time. So let's just first get into the one-dimensional transversals. And the first slide I'm putting up is going to be very complicated because I already start with these m parameters L and n. So let me just start with the two-dimensional case, which is essentially a matrix. Everybody knows what a matrix is, right? So what you want to do, you have a matrix. Of a certain size, and for both directions that exist, the rows and the columns, you have a parameter. Say 2 in the row direction and 1 in the column direction. That means that this is the maximum number of ones you are allowed to put in this matrix. I want to have a 0, 1 matrix. So let's just be greedy here. I'm allowed to put 2 here. Oops, this column is done. This column is done. I can go on with this. I'm allowed to put 2 more here. This column is done. This column is done. I only have these guys. I'm allowed to put 2 more ones here and here, but I can no longer go on. But I can put at least one here and nothing else. Agreed? So this is a way of satisfying these conditions. Have I done as well as I could have? What do you mean by as well as I could have? Have I put in as many ones as possible? But I will tell you that yes, under these conditions I did. I see a couple of no's, but under these conditions I did. Because let's just think, in this direction, in every line I can put in 2 ones. So if I look at this way, I have 4 lines, 2 ones for each. I can put in 8 ones and no more, right? But if I look at the columns, I can put 1 ones in each column, and I have 1, 2, 3, 4, 5 columns. So the columns don't allow me more than 5 ones. In the entire matrix, and I do have 5 ones in there. So this is sort of the idea I'm talking about. You have these arrays, they are not necessarily 2-dimensional, they may be 3-dimensional, 4-dimensional, 5-dimensional, and so on. And for each direction, you have a parameter that tells you, I have to put in this many ones here. Or not I have to, I'm allowed to put in this many ones here, not more. How best I can distribute my ones? That's the question. That's what I'm talking about. N plus 1 is going to denote, for historical reasons, not N but N plus 1, the size of each line in each direction. L is going to denote how many entries I would like to put in there, how many entries. And I will arrange my indices in this order. This is just convenience. These 2 guys belong together. It doesn't matter which one I consider the first one, the second one, the third one. So I have something to handle with the order of these things. These are the numbers I have. For that case, I would have 2 over 5 and 1 over 4. Because the L numbers are 2 and 1, the N numbers are 4 and 5. The N plus 1 numbers in this case. So I have these parameters, and for convention I want to order them in this way so the ratios are increasing. And I have an m-dimensional array of zeros and 1. M is 2 over there because I have a 2-dimensional array, that's what a matrix is, but I'm allowed to have higher numbers. And a line in the jth direction, in an m-dimensional array, will be just a collection of entries where every entry is fixed except the jth one. In 2 dimension, what happens? You have 2 entries. One of the entries is fixed, the other one can go. That will give you all the lines and the columns. In j dimension, this is how the generalization looks like. And I'm going to call this 0-1 array an L1 LM transversal. Now notice that the sizes here are how many numbers the entries are allowed to take in the positional direction. These are the L numbers at the top. I'm going to call it in an L1 and a transfer ball. Ignore the JS direction contains more than S sub j non-zero entries. This is exactly what I told you. For every direction, I am told what is the maximum number of ones I give. So, clearly, blah. What does it mean? I add up all the entries in the matrix. And I'm doing what I told you. I fixed the JS entry. Sorry. I fixed which entry I'm allowed to vary. All the rest of the entries are fixed. So each of the lines in the JS direction can have L sub j elements in it. So how many different j directional lines I have? How many different j directional lines and many different ways I can fix those coordinates? The ks coordinates can be fixed in L sub k plus 1 differently because that's the length of the array in that direction. So if I want all those possibilities, I just have to multiply all the values N sub k plus 1 for all k's that are not equal to j, because those are the places where I'm allowed to fix my coordinate. And I can just write in L sub j divided by S sub j plus 1 instead of L sub j, and in this case I have this product coordinate. Why I wanted to do that? Because now this is a constant. This is just the total number of entries in the matrix, and this is the parameter that actually gives me a bound. So this fraction of the total number of entries in the matrix I'm allowed to have in an L1 transversal. And obviously, in that, depending on which j I'm choosing here, I could choose any one of the j's, I have a different upper bound. But only one of them matters, the smallest one, because the rest of them give me a worse one. Over there I have 8 and 5. I cannot have more than 8 and I cannot have more than 5 ones in the matrix. Obviously 5 is the maximum number I can have there. So the smallest one is the one that matters. So, oops, sorry. And I'm going to call my transversal 4 if that sort of thing happens over there. I have put in the maximum number of one entries allowed, so at least in the first direction, every line contains precisely as many entries as it can have. So, I can look at the transversal in a different way, and it actually turned out to be useful, so that's why I want to talk about this. So, now what I'm going to do, I'm going to just look at the one entries in the matrix, and I'm going to look at the position, the coordinates that give me that one entry. So, really, it really doesn't matter whether I have the matrix or I know exactly where it has the ones, because the rest of the places it has a 0. So obviously it's the same thing that I'm looking at here. But what happens here? Now, I choose my favorite j, my favorite direction. And I write up all these entries when I have my one entries. I remove the JS entry, I cover it up. So what happens? I can look at j-1 directional vectors. Those are the positions where I have the ones in the matrix. So if I have the same coordinates repeating in every position, that corresponds to the same line. So each and every m-1 tuple here, if I cover up one of these things, can appear at most L sub j times. So if I have this collection of entries that have the property that I'm covering up the JS column, each and every entry appears no more than L sub j times, I have something that corresponds to a transversal. This is a very, if the transversal is full, then equality holds for the first direction and whenever those parameters give the same number. So if I look at these subsets of M tuples, I again have a transversal. So Füredi-Briggs-Obnisco and Shearer, in connection with the Sperner theorem, which I'm not getting into, has shown that in 2 dimensions, you always have the full transversal. I've just showed you one over there, but it doesn't mean that for every possible combination of line length and parameters that I give over there, you can make it in such a way that it contains the maximum possible number of ones that's allowed by these conditions. Füredi-Briggs-Obnisco and Shearer has shown that it is actually always possible. However, their proof uses matchings or flows. a concept that's interchangeable here, and those concepts do not exist to higher dimensions. So the question was still open. If you have an m-dimensional array with the parameters given, can you always make a full transversal? So that's what I'm going to talk about first. So I'm going to tell you I have one, and I will actually prove it. Pick your favorite real numbers. These are alpha, beta, and mu. Anything. I'm going to give you some conditions here. Beta and mu has to be positive, or non. Mu has to be positive, beta can be 0. This condition says that beta plus mu is at most 1, essentially, this one. Alpha is anything. Fix your positive integer m. And I'm going to do the following. I count the number of non-negative integers from 0 to n plus 1 possibilities here, by the way, which has the following property. If I take I over n plus 1, add it to my fixed alpha that I chose up here, this thing denotes the fractional part. So the number minus the floor of that number, somewhere between 0 and 1. And look at in how many of the cases this fractional part falls into this interval beta plus mu. And I want to count how many of those integers actually have this property. But the theorem says that this quantity falls between the floor and the ceiling of n plus 1 times mu. Which means that when n plus 1 times mu is an integer, the floor and the ceiling are the same, I know exactly what this number is. And when n plus 1 times mu is not an integer, well, the floor and the ceiling has only a difference of 1. So it's either this value or that value. The conditions I have for beta and mu ensure to be two things. This interval beta and beta plus mu falls in the interval 0, 1. That's why I need to have, because the fractional part falls into the interval 0 and 1. So that's why I have the conditions of beta and mu, so this actually makes sense what I want to count here, and alpha can be anything. So I can rewrite this statement as this number, the number of i's that fall, that satisfy this property, actually take one of these two values. Now, as I said, I'm going to prove this. So what I'm going to do, I divide the interval beta plus 1. See, this is beta plus 1. Beta plus 1 is longer, because this interval has length mu, and mu was less than or equal to 1. So I have an interval of length 1, and I'm going to divide it into n plus 1 intervals, n plus 1 subintervals. So it's beta plus 1 over n plus 1, beta plus 2 over n plus 1, and so on. I took the number line and I put it in a circle which has circumference 1. I have n plus 1 subintervals of equal size. Okay? So the next thing is what I wanted to have. I wanted to count the integers I such that the fractional part of alpha plus I over n plus 1 falls into a certain interval. Well, I look at these numbers, alpha plus I over n plus 1 for all possible values. Since I put my number line in a circle of circumference 1, they fall somewhere in here too, and they fall into the appropriate part because this thing has length 1, so the integer differences disappeared, and that's all I needed. When I consider the fractional part, the integer differences disappear. So each and every one of these guys, since they have the same distance as the beta numbers, 1 over n plus 1, fall into the same position of those black intervals. So what happens, I have these n plus 1 numbers, and they fall into the same position of these intervals. They are equally spaced. Now, so I want to know how many of these fall into the interval beta plus mu. So essentially I have to count how many intervals are in this new length interval. Well, the interval interval is length mu. The subinterval is the length 1 over n plus 1. So I divide mu with 1 over n plus 1, which means I'm multiplying by n plus 1. If I take the floor of that number, that many intervals fall entirely within my interval of length nu. So each and every one of them contains a point. I must have at least this many points in there. And if the ceiling is larger by 1, my interval of length contains a part of that extra interval too. My extra point in there may or may not fall within my interval, so possibly I have this many points, no more, and I have at least this many points. We are done. We proved our number. So what does it have to do with full transversal? Give me your parameters as you want. Choose mu to be the smallest one of the L over n plus 1 numbers. And pick your favorite beta and mu in such a way that they satisfy the condition that I did for my lemma before. And do the following. Take all those entries from the entries possible that have this property. I add up the entry I sub j divided by n sub j plus 1 for all the n values. I get a number. Take its fractional part and take only those entries where this fractional part fall into this interval of length mu. I claim this is going to be a full transversal for m-dimensional parameters. And I will give a proof for that. So let's remember that mu was the smallest of the L over n plus 1. So what happens now? Oops. So if I compute mu times nj plus 1, replace 2 by nj plus 1, it's at most L sub j. And when j equals to 1, mu times n1 plus 1 equals to L1. I will use these things. So what do I want to do? I want to check whether this is a transversal. If this is a transversal, if I fix all but the JS entries, and count how many I have of those, I must have at most LJ. Let's think about that. So fix the JS entry, fix J, and fix all the other entries. I'm going to choose alpha to be the sum of the I numbers divided by the n plus 1s, where I sum over all entries which are not equal to J. Why is this good? Because this quantity, which I used in the definition of the transversal, is going to be precisely alpha plus this ratio for the JF entry. So what does that mean? I want to count these numbers where only the JS entry is allowed to change, all the rest is fixed, and the JS entry is from 0 to nj. And I want to count the ones for which the fractional part of this quantity was in this interval, because that was how I defined my transversal. So basically I want to count those guys where alpha plus ij over nj plus 1 falls into my interval. And I have this lemma that says that there are no more than this many of them. This number is less than or equal to lj. This number wasn't an integer, lj was. That means that even the ceiling of this number is at most lj. That's exactly the condition I had to check to know that this is actually a transversal. I claimed it was a full transversal. What makes it a full transversal? For j equals to 1, I do not have less than or equal to here, I have equal. Then for j equals to 1, this is an integer, and it actually equals to this, so I'm done. And my lemma says that when the number that I put in here, in the ceiling, is an integer, I actually have equality here. And now it is an integer. So it actually is a full transversal. So we have managed to find full transversals for all possible parameters there is. Not just in 2 dimensions, but in any dimensions. So, some remarks. Where can my I1, I2, I3, I4 numbers come from? I1 came from here, I2 came from here, I came from here. N plus 1 choice, N1 plus 1 choice, N2 plus 1 choice, N plus 1 choice. So the total number of choices are this. My full transversal contains precisely this many elements. I showed you that earlier. So what's the ratio of these two? These two are the same thing, so they cancel. It's N1 plus 1 over L1. So if I take this guy and I try to partition it into full transversal, meaning I try to make disjoint sets that define for me a full transversal, I can put in at most N1 plus 1 divided by L1 floor many of them. Can I do that? Well, actually, using what we have just said, I don't even need to read it, I can easily do that. Because I know that I take an interval that has of size L1 over N1 plus 1, that's what my theorem said. And I take the entries for which the fractional part of this quantity falls into that interval of L1 over N plus 1 size. Well, I take the interval 0, 1, I chop it up into as many parts as possible of this length intervals, I can do that. And I might have some little leftover. I take the entries for which the fractional part of this quantity falls into that interval. Where the interval size equals to L1 over N1, which is true for precisely this many of those, I will have a full transversal, I know that. If I have a little leftover interval, that won't be a full transversal, but that still will be a transversal. So what we have managed to argue at this point is that we can partition the set of possible entries here into as many full transversals as possible, plus perhaps a little leftover cell that's not a transversal, it doesn't have enough entries. Well, that's not a full transversal, sorry. It doesn't have enough entries, but it is still a transversal. So, apart from that mysterious Sperner theory that I haven't talked about, why do we care? We care because, as it turns out, these things are orthogonal arrays. So I'm going to give you the definition, and it's going to sound very weird. So I have a set of non-negative integers. I have some R different set of symbols, and I have a capital N by R matrix, so it has R columns and some unspecified number of N columns. And the ith column has to have elements from the set Si. So I have my matrix over there, but I have even something more weird. Each column has its own set of entries that can come in. And I will call this T a mixed orthogonal array of strength D. Constraints are index at L. Well, the L, I know what it is. R is just the number of columns. These strengths, I don't know what it is yet. But it means that if you take any set of D different columns, and any symbols that can appear on those columns, and you count how many times in a line precisely those symbols appear in precisely those positions, then they will appear the same number of times for this particular choice. And this number is coming from L. And if the ratio of the N plus 1 over L numbers are the same, then the full transversal is precisely a mixed orthogonal array of strengths. N minus 1 constraints M index set of the L numbers. Si is from 0 to N minus 1, and N is the number of bonds in the matrix. This can be proved, but let me show you what an orthogonal array is, because I'm pretty sure you have no idea after I put all that up. Let's just say this is a 12 by 5 matrix, okay? And if you look at it, the first column has entries 0, 1, 2, so the first set is 0, 1, 2. And all the rest of the columns is entries 0, 1, so all the rest of the sets are 0, 1. So I have 12 rows, these are quadrants, this was the N number. Constraint, the number of columns is 5. I claim the strength is 2. And my index set is 2 and 3. Let's just see. Entries in the first and in any other columns can be, well, the first column can have 0, 1, 2, and any other column has a 0 and 1, so these are the possible entries. If you take any two columns here that includes the first, and count how many times these symbols appear there. 0, 0 will always appear twice, 0, 1 will always appear twice, 1, 1 will always appear twice, and so on. 1, 2, 3, 4, 5, 6 times 2 is 12. The number of rows is right. If you want to, you can do the counting. But this works out. If I take any other two entries, well, 2 cannot appear, so I have the entries 0, 0, 0, 1, 1, 0, and 1, 1. Each of those, if you select those two columns, will appear 3 times. Numbers should work out because this has 4 possibilities. Each appearing 3 times is 12, so I have exactly as many as I have. This is what a mixed orthogonal array means. A very nice structure that has these properties. Okay, so this is what we are looking for. Why are we looking for? Because they are very important. They appear in error-correcting codes, locating arrays, block designs, group testing, frame-proof coding, hash file hashing families. They are needed to learn a sparse Boolean function. They appear in compressed sensing. And let me get back here because this is the easiest one to explain. For statistical reasons, if you want to have a statistical experiment, you might have different levels of the experiment. For example, you want to do something with a plot of land. You want to see how the acidity of the soil, the amount of water available, the amount of sunshine, and a couple of other things affect how the plants grow in there. So for each of those things, you have different levels. That's your sets. The acidity can be, say, 0, 1, 2, 3. The sunshine level can be between 5 and 7. Those are your entries. And you want to design an experiment that each possible combination appears roughly the same amount of times. For statistical purposes, this is something very desirable. Your statistical experiments will have more power in some sense if you manage to do this. And therefore, you want something like a mixed orthogonal array. I'm running out of time, so I'm not going to say any more about this, but I want to say that there was one problem with what I just put up. I've had m levels, and the strength was always m minus 1. So the next question that should come up is, how can you design things that don't just have strength m minus 1, but different strengths? And in order to do that, you have to extend the concept of transversals to something that's called a d-dimensional transversal. This can be done. This will provide you with orthogonal arrays of different strengths, all sorts of nice goodies just as before will work out, and essentially the same idea works in designing full d-dimensional arrays. You just have to put a few more twists on it. And since I'm out of time, this is where I finish. Thank you very much.
Do you have any questions for the speaker? So let's thank you again.